Hi. So we're going to continue on the tutorials with a discussion of the Navies Stokes equation, where we will introduce this fundamental equation to fluid mechanics, which has four basic terms: inertial forces, pressure forces, viscous forces, and external forces. The usual symbols applied are mu for fluid flow dynamic viscosity. This is an engineering way of writing it. Usually we write it as eta in biophysics physics. Rho is the fluid density, P is the fluid pressure, U is the fluid velocity. As it so happens from our discussions of low Reynolds numbers, inertial forces disappear, become zero at very low Reynolds numbers, which means viscous forces dominate, and external forces and viscous forces combine with pressure forces to define everything that we can observe. This law is derived from the conservation of momentum of fluid parcels and combined with the continuity equation, that is the del P del rho del by del T plus gradient of rho U is equal to 0, serves to help us solve any fluid equation in a bulk sense. The partial derivative and the gradient of density at velocity sum to 0. This is the meaning of this continuity equation, and it's a conservation of mass, indicative of conservation of mass. So together with the boundary and initial conditions, they form the foundation of computational fluid mechanics, or CFD. And you will see sometimes calculations of jet engines and flows around a cheetah, or flow dynamics around new cars. All these are computational fluid mechanics outputs and very important for engineering, and maybe not as widely explored in biology, but definitely the basis of a lot. Now, for our purpose, we have discussed earlier also that Reynolds number differences make a difference to the streamlines that we can observe. And to get at some answer with this, we had defined kinematic and dynamic viscosities, nu being the symbol for kinetic and eta for dynamic, rho density, U velocity, L characteristic length scale. So Lu by nu, or Lu rho by eta, because nu is eta by rho. Now, the question that arises is, what is meant by characteristic length scale? So for a flow in a cylindrical tube along a certain length with a certain pressure drop between the start and end of the tube, L is the length of the tube. For a bacterium swimming in a bath, L is the size of the bacterium. And we have discussed this before, but the typical size scale of E. coli bacteria is 2 microns, and we say microscopic organisms are of bacterial type prokaryotes, typically in the range of a few micrometers. That is L. U is the velocity, so how fast it moves. At a microscopic scale, the velocity is around tens of microns per second. Rho, which is the density of water, is in SI units 1000 kg per meter cube, and eta, as we said, is 1 by 1000 Pascal second. So plugging these in, we end up with low Reynolds numbers for bacteria. But what about other organisms? What about large organisms, not single-celled, but multicellular metazoans? So as it turns out, that the length scale, as we said earlier, or size, and the traveling speeds scale. Evidently, we expect that larger animals are able to swim faster. It's typically true. For example, a killer whale travels at tens, if not 20 meters per second, whereas a bacterium does only 20 microns per second. Now you can, of course, divide out the length scales and try to ask what the relative body length covered time is. But if you're looking at absolute velocities, then indeed the bigger organisms move faster. Birds fly faster than insects, shrimps swim faster than sperm cells, and so on and so forth. Now, in this graph, what you're looking at is that low Reynolds numbers and viscosity dominate at small length scales, single-celled, at some intermediate size and velocity scale. Reynolds numbers are influenced in the range of 10 to the power 0. There's 1 to 10 to 100 to 1000. Both the viscous and inertial components dominate. And at high Reynolds numbers, that is 10 to the power 6 and so on, only inertial numbers dominate. Viscous drag is not that important. We also refer to it as inviscid regime. This is a figure taken from Klotzer and Company, Klotzer in 2019, a review in Soft Matter. So if you focus from a quantitative cell biology perspective or a cellular biophysics perspective, then of course we're looking at 10 to the power minus 3 minus 6 Reynolds numbers. And this was what was illustrated in our previous discussion, if you recall, of the ratio of inertial to viscous forces being expressed as Reynolds number. And with a known velocity, for example, bacterial versus human swimming, the Reynolds number is 10 to the power minus 4 for bacteria and 10 to the power 4 plus 4 for humans. So humans of meter scale, 10,000 value of Reynolds number, and for bacteria, 1 by 10,000. Yeah? You could say 8 orders of magnitude difference. Just to remind you that the Stokes drag force and Reynolds number are related to each other, and we had gone over the Stokes drag force for a spherical object, with F being force of viscous drag, R being radius, U being velocity, and theta being dynamic viscosity. Because in fact, Reynolds, that is Osborne Reynolds in 1883, showed experimentally that the motion of water shall be direct or sinus in certain circumstances, and these certain circumstances were the part where he discovered that high Reynolds numbers or values of R high in the high range lead to smooth flow, whereas low range lead to turbulent flow. And that was due to drag. So you could argue that the drag force and Reynolds number are related to each other. And this is illustrated by this example that we had discussed earlier too, of streamlines. Sorry, so high Reynolds numbers are turbulent, low Reynolds numbers, I misspoke. So I hope you've noticed this. Yeah. So Stokes' law, we have gone over this earlier, and to remind you, for an ideal spherical object can be derived, expresses the force drag on a sphere of radius r and eta fluid viscosity v being the speed. Let us try to see if we can calculate the Stokes drag force for a bacterium. So we say that F is equal to 6 pi into eta, which we want to use as SI units, is 10 to the power minus 3 Pascal second. R for a bacterium is micron scale, so 10 to the power minus 6 meters. V is 30 microns per second. So we say again tens of microns per second. So we end up with F is approximately equal to, we said, 10 to the power minus 3, minus 6, and minus 5. So minus 9, minus 5 is minus 14. So it is 6 pi, which is 6, 3, so 18. That's about, F is approximately equal to minus 3, minus 14 we said, plus 1, 10 to the power minus 13, which is approximately 0.1 piconewton. This is the approximate force that we expect a bacterium swimming in a water environment will experience, moving at around 10 micrometers per second in water which has viscosity 10 to the power minus 3 Pascal second. So interestingly, while for spherical objects, which is what we did right now for bacteria, we can calculate easily a drag force. For non-spherical objects, things get trickier. And it is important to bear in mind that cell shape is quite diverse. In fact, if you look only at human cell shape diversity over here in this image, you will see a dramatic difference between smooth muscle cells, blood cells, bone cells, sperm cells, fat cells, ova, nerve cells. So the size difference. So the longest axon of a nerve cell, the spinal cord neuron, can be a whole meter long. Smooth muscle cells, 30 microns, 40 microns, spindle shaped. Blood cells can be in tens of micrometers in length. So all this indicates that there may be a reason to think about shapes other than spheres and all. So for non-spherical shapes, we need to consider something called the drag coefficient, CD. And the drag force calculation then becomes a little more complex. We have half into rho into u square CD times A, where A is the reference area. So V and U are used interchangeably. I've just corrected it. The shape-dependent drag coefficients are in terms of numbers that are dimensionless. And you should always check that the right-hand side gives you force units and dimensions. These values change depending on the cross-sectional area. Where do you find these numbers? Typically in engineering handbooks. Standard values, they are empirically found, namely by doing experiments.